Hello students, welcome back to our class on ring theory. Today we will discuss subring of a ring. We will give examples of subring. We will see how to test whether a given subset is a subring of a ring or not. And we will also see some theorems related to the intersection of subrings. Okay, so let us begin. A non-empty subset S of a ring R is said to be a subring of R if it is itself a ring with respect to the same operations as in R, right? A non-empty subset S of a ring R is said to be a subring if it is itself a ring with respect to the same operations as in R, okay? So with respect to the same operations in R, if a non-empty subset is also showing or satisfying all properties of the ring, then it is called a subring of R. Okay, for example, we will see that the set of integers with respect to addition and multiplication is a subring of the set of rational numbers, the ring of rational numbers with respect to addition and multiplication, and which is again a subring of the set of the ring of real numbers with respect to usual addition and multiplication. Okay, we will see some other examples as well. Okay, so let us start with this theorem, which is a theorem for testing whether a non-empty subset is a subring or not. Okay, so it's known as a subring test. So a non-empty subset S of a ring R is a subring of R if and only if S is closed under subtraction and multiplication. That is, if and only if A minus B and AB belongs to S for every A and B in S. Okay, means you take any arbitrary elements A and B inside S. If A minus B as well as A into B belong to S, then we can say that S is a subring. Okay, so we don't need to test all those nine properties for testing whether a ring is a subset is a subring or not. Okay, it is just sufficient to check closure property of multiplication and this the property of subtraction A minus B. Okay, right? So let us see how we can prove it, and this proof is also important from the exam point of view as well. So first let S be a subring of R. So there are two parts, as you see in this theorem. If and only if S is a subring, then this condition is satisfied, and the other way, if these conditions are satisfied, then S is a subring. Okay, so first let S be a subring. Okay, then we have to show that the given conditions are satisfied. So that's quite simple. Then S is a ring with respect to the operations in R. Okay, by definition. So S plus, so if S is a ring, then S plus is an abelian group. Okay, so if we take any two elements in S, then since S plus is an abelian group, so minus B also belongs to S, right? So A plus minus B, that will be an element in S because S is closed with respect to addition. Okay, so A minus B is in S, right? So also since S is a ring, so S is closed with respect to multiplication as well. Okay, so AB belongs to S. So given any elements A and B in S, we have A minus B is in S and AB is in S. Okay, so this part is quite obvious. Conversely, let S be a non-empty subset of R satisfying these two properties. Okay, S is any non-empty subset which satisfies these properties, and that whenever you take A and B inside S, you also have A minus B and AB inside S. Okay, so to prove, let us prove it. To prove S is a ring with respect to the same operations as in R. Okay, so here the proof is little bit different from what we have been proving step by step. In case we want to show something is a ring, we usually first show that it's closed under addition. Okay, and then we test the associative property. Okay, then the existence of inverse. Okay, here we will start from the existence of inverse. Okay, from the existence of zero element. Okay, first we will show that the zero element belongs to S. Okay, because we need to show that S is S is already given to be non-empty. So since S is a ring, it should have the zero element. Okay, so we can show it by the condition that S is a non-empty subset. It is given that S is non-empty. Okay, so there exists an element. Since it is non-empty, it will have some element, say X belongs to S. So by the given condition, what we can write? We can write that x minus x is an element of S, right? Because if a, b are any element of S, then a minus b is also inside S. So in particular, if x is an element, then x minus x has to be inside S. But what is x minus x? By property of ring, it's 0, where 0 is the 0 element of R. Okay, thus S has the 0 element. Okay, so the non-empty subset S has the 0 element. Then we will show that existence of additive inverse. So we start with any element of S. Then since 0 is in S, already 0 is in S, so by given condition 0 comma a belongs to S, this will imply that 0 minus a belongs to S. Okay, that means 0 minus a is just minus a, that is the additive inverse of a. So each element in S has its additive inverse also in S. Okay, so every element in S has its additive inverse. So this is another condition. Next I have to show that, so using the above two, we will show that it is closed under addition. So let a and b belongs to S be any element, then S shown above minus b also belongs to S, and by the so we have a comma minus b belongs to S, and by the given condition we can write a minus minus b is in S. Okay, but minus of minus b is inverse of minus b, additive inverse of minus b is plus b, so it's just a plus b, right? So we have shown that if we start with any two elements of S, then their sum is also in S. Okay, so we have shown that S is closed under addition. Next, S is closed under multiplication. So this follows by the given condition itself. Okay, the condition itself says that S is closed under multiplication, because if you take any two elements a, b in S, the condition says that their product is in S. Okay, so next we need to verify just the other properties. So other properties we can write it this way: let a, b, c belongs to S be any elements, then a, b and c are also elements of R, right? Because S is a subset of R, every element of S is in R. Okay, and so all these properties will hold. These properties just require the concept that these elements belong to R. R is already a ring, so it will satisfy this associative property of addition, commutativity of addition, associativity of multiplication. Okay, then this is the left distributive and this is the right distributive property. Okay, all these properties will be automatically satisfied because every element of S is also an element of R, and R is already a ring, so these properties are satisfied. Okay, so thus S is a ring with respect to the operations in R, and hence S is a subring of R. Okay, so we have proved the theorem. So note that in any ring R, the subsets 0, singleton 0 and R are always subrings. Okay, so the ring itself is a subring of itself, right? And the ring containing the 0 element, only the 0 element is also a subring. Why? Because if we take S equal to singleton 0, then we have 0 minus 0 belongs to S. Okay, so every element of S satisfies these properties. Any two elements taken from S satisfy these properties. If we take any two elements of S, we are ultimately taking two zeros, right? So 0, because 0 is the only element here, so 0 minus 0 is 0, it satisfies, and 0 into 0 is 0, which is also inside S. So singleton 0 satisfies all conditions for being a subring. Okay, so it's a subring, and R is itself a ring, and R is a subset of itself. So every set is a subset of itself, right? And R is already a ring, so that means by definition R is a subring of itself. Okay, so every ring is a subring of itself, just like groups, every group is a subgroup of itself. Okay, so these are trivial. Okay, so these are trivial subrings. R and 0, they are called trivial subrings or improper subrings, and any subring of R other than R and 0 is called a proper subring. Okay, so any subring which lies between these two is a proper subring. Okay, so let us show the example. Show that the set of integers is a subring of the ring of real numbers with respect to usual addition and multiplication. So this is very simple, just I have taken it to explain you the concept. So we have so first of all we have to show that Z is non-empty. So the set of integers is non-empty because there are so many integers existing. So we just need to find one integer. So one most obvious integer is 0 itself. So 0 is an integer and 0 belongs to Z, so Z is non-empty. Okay, And if we take any two elements of z, then difference of two integers is in integers. These are by properties of integers. So a minus b belongs to z, and the product of any two integers is also in integers. So it satisfies, by the Subring test we can show that z is a subring of R. Okay, right. But you see there are some other sets which are not subrings. The set I of irrational numbers is not a subring of the ring R of real numbers with respect to usual addition and multiplication. Okay, the set I of real numbers is not closed with respect to addition, because if we add two real numbers, if we add two irrational numbers, we may not get an irrational number. Okay, so for example, very simple example, root 2 is an irrational number, minus root 2 is also an irrational number, right? But root 2 plus minus root 2, it is not an irrational number. Root 2 plus minus root 2 is 0. 0 is a rational number. Okay, so the set I is not a subring. It is not closed with respect to addition. Okay, if it is a subring, it has to be closed with respect to addition, multiplication, etc. Okay. Okay, next we come to this theorem. Intersection of two subrings of a ring is a subring. If you take two subrings and then take their intersection, then you get another subring. Okay, so we start this way. Let S1 and S2 be two subrings of a ring R. What I have to prove? We have to prove that S1 intersection S2 is a subring of R. Okay, so first of all I have to show that S1 intersection S2 is non-empty. Okay, and what is the easiest way to show this? Easiest way is you find out one element inside S1 intersection S2. Okay, so we already have that S1 and S2 are subrings. Okay, S1 and S2 are subrings of the given ring. So S1 will contain the 0 element, right? And S2 will also contain the 0 element. That means the 0 element 0, which it belongs to both S1 and S2. So that means 0 belongs to their intersection. So the intersection is non-empty. So S1 intersection S2 is a non-empty subset of R. Okay, and let A and B belongs to S1 intersection S2 be any element. Okay, and then A comma B belongs to S1 and A comma B belongs to S2 by definition of intersection. Okay, intersection of two sets contains only those elements which belong to both the sets. Okay, so whenever we write AB belongs to S1 intersection S2, we can immediately write AB belongs to S1 as well as AB belongs to S2. Okay, so this will imply A minus B and AB belongs to S1 because S1 is a subring. Okay, and just now we have done the criterion for subring. Right, so since S1 is a subring, the difference of any two elements and the product of any two elements will belong to S1. Okay, since S2 is a subring, A minus B and AB, they also belong to S2. Okay, so we have A minus B and AB, they belong to both S1 and S2. So A minus B and AB belongs to S1 intersection S2. Okay, and thus, so once we get this condition, we can immediately conclude S1 intersection S2 is a subring of R. Okay, then we have a very similar theorem. Intersection of a finite number of subrings is a subring. Okay, if you have more than two subrings, okay, S1, S2, S3, S100, okay, as many subrings as you want, you take their intersection, it is going to be a subring. Okay, so the proof is very similar except some notations. So let S1 and S2 up to Sn be subrings of a ring R. To prove that intersection I goes from 1 to n, Si is a subring of R. Okay, so we have for each I equal to 1 to up to n, Si is a subring of R, right? So hence 0 is in each Si is a subring, so the 0 element will belong to each Si. So we can write hence 0 belongs to Si for all I equal to 1 to up to n. That means what? 0 also belongs to their intersection. So 0 belongs to intersection I goes from 1 to n Si. Okay, that means intersection I goes from 1 to n Si is non-empty. Okay, so now you take any two elements inside intersection I goes from 1 to n Si, then we will have A comma B belongs to Si for all I. Okay, by definition of intersection. Okay, if these two elements belong to the intersection, they have to belong to every set. Okay, so and since each Si is a subring, so we have A minus B and AB, they belong to Si for all I, right? And from here again I can conclude A minus B and AB, they belong to intersection I goes from 1 to n Si. That means intersection I goes from 1 to n Si is a subring of R. Okay, so this is what we have shown. Next, another similar theorem for the intersection of subrings. Arbitrary intersection of subrings is a subring of R. Okay, now if you take infinitely many subrings, anything, any collection of subrings, then also their intersection is also a subring. Okay, so let S lambda such that lambda belongs to capital lambda. This symbol is called capital lambda. Okay, uppercase lambda. So let the set of S lambda such that lambda belongs to capital lambda be any collection of subrings of a ring R, where lambda is a non-empty index set. Okay, so if lambda is empty, there the empty intersection is actually the whole ring. That is a convention. Okay, so we don't need to take that into account. So we can start with lambda as a non-empty index set. Okay, so to prove that intersection lambda belongs to capital lambda, S lambda is a subring of R. Okay, so we have for each lambda in capital lambda, S lambda is a subring of R. Okay, so 0 belongs to S lambda for every lambda, right? And so 0 belongs to their intersection lambda belongs to capital lambda, S lambda. So that means this intersection is non-empty. Okay, this intersection is non-empty. And now let A comma B belongs to this intersection, be any elements. So A and B will belong to each S lambda. Okay, but each S lambda is a subring of R. Okay, that means A minus B and AB will be inside S lambda for every lambda, right? So A minus B and AB, they will be inside intersection lambda belongs to capital lambda, S lambda. Okay, thus intersection lambda belongs to capital lambda, S lambda is a subring of R. Okay, so arbitrary intersection of subrings is also a subring. Okay, right. So this was all for today. In the next lecture, I will also show you that the union of two subrings may not be a subring. Okay, and we will consider some more examples of subrings. Right. So till then, thank you.